Hi, my name is Edoardo Contente, and today I'll explain you the Higgs boson. So, first of all, I have a question. What is this made of? And I mean, everything. What are these trees, plants, grass, dirt, air, light truly made of? I mean, of course, trees are made of wood, and plants are made of cells, but if we go further, if we look each time more closely, what are the true fundamental constituents? So, you probably heard about the atom and their famous not exact depiction, but atoms are not fundamental. They have their constituents called protons and neutrons at the core and electrons orbiting around. And protons and neutrons are also each one made of three smaller particles called quarks. So, if we put these and other known particles in the same description of the universe, we might get the true fundamental constituents. So, what you are seeing is called the Standard Model, and it is the most general accepted description of the universe. It has fermions, particles with mass, which include all types of quarks, electrons with its heavier and lighter cousins, and bosons, force carriers, which make the fermions interact with each other through the four fundamental forces: electromagnetism, gravity, weak force, and strong force. And we have a special type of boson called the Higgs boson. So all is made of particles, but what I didn't tell you is that in modern physics, particles are viewed as small vibrations in a specific field. A field, by definition, is something that has a value in every point in space. So an electron is actually just a vibration in the electron field, and a quark up, a type of quark, is only a vibration in the quark up field, being that a point in which the field doesn't vibrate simply doesn't correspond to any particle. For most of the fields, the electron field, quarks fields, force carriers fields, the average value in empty space is 0, because that's their lowest energy configuration. I say average because in quantum physics, there is always some uncertainty. What can I say? Nature is lazy. But for the Higgs field, the field in which the Higgs boson is an excitation, the average value in empty space is not 0. It is a non-zero stable value. Why? No one knows. But if you heard that the Higgs boson is the big deal and that it gives other particles mass, it's completely wrong. Because what is important and what actually gives other particles mass is the Higgs field, in which the Higgs boson is just an excitation. The Higgs boson by itself doesn't have much significance. It is just a vibration of the Higgs field around its common value, which in this case is non-zero. But what process actually gives particles mass? Well, before that, let's analyze what is mass. Mass is by definition resistance of motion. So if you give more energy accelerating an object, it has a bigger resistance of motion, and thus it's more massive. Take the example of a car and a huge truck. A huge truck is harder to accelerate. It is more massive. But what about massless particles? Well, they simply don't have any restriction. They don't have any resistance of motion, so they must always go at the fastest speed possible, the speed at which light goes, because it's made out of massless particles. But do we really need a field that gives other particles mass? Don't particles have just mass? No. And the thing is, if the Higgs behaved like other fields, in which its value in empty space would be 0, then all particles in the Standard Model would be massless and always travel at the speed of light. So what actually makes these particles acquire mass is the Higgs field's value in empty space. This process is called the Higgs mechanism. So how does the Higgs mechanism give other particles mass? Well, that has to do with symmetries. Symmetry is the quality of not changing appearance after transformation occurs. Take the example of a rod. A rod has a symmetry. We can rotate it, apply a transformation, and it won't change its appearance. So, when Higgs field is 0 in empty space, nature behaves more or less like a rod. There's a symmetry that makes some particles interchangeable, and all particles are massless. But when the Higgs field chooses a value in empty space, that symmetry is broken. And what do I mean by that? There are two types of symmetry break. spontaneous symmetry break, and explicit symmetry break. So if we transpose that to the rod example, we have an explicit symmetry break in which the rod bends by direct force, and we have a spontaneous symmetry break, which is the case of the Higgs mechanism, in which the rod bends by applying a force in the direction of the axis of rotation. But how does this complicated process translate in different masses? There are electrons with its heavier cousins and lighter cousins, there are many types of quarks with different masses, and there are also massless particles like the photon, the particle of light. There's a simple rule. Remember that all is made of fields. Well, it just so happens that after the Higgs spontaneous symmetry break, some fields interact more with the Higgs field and give rise to heavier particles, some fields interact less with the Higgs and give rise to lighter particles, and some fields don't interact at all and give rise to massless particles. So, a particle's mass is proportional to its interaction with the Higgs field. But as I stated before, the Higgs boson also has mass, but it comes from a more intricate process and not from the Higgs field. Other particles don't have mass originally because of a prohibitive symmetry, but the Higgs boson simply has mass because there's no reason why it shouldn't. But still, a question persists. Why do some particles and their underlying fields interact more with the Higgs than others do? No one knows. Wait, why is it called the Higgs boson though? We know it's a boson, a type of particle, but the name Higgs comes from Peter Higgs, who was the first one to publicly propose the boson in 1964. Although the Higgs mechanism was also proposed by many other physicists at the time, the name Higgs mechanism stayed in a quite unfair way. But the Higgs boson still holds some importance today. It's a consistent proof that the Higgs mechanism exists, and it's a new window for physicists to discover more about weird things like dark matter and find out more about the mystery surrounding the whole Higgs idea, like why is the Higgs field value in empty space non-zero, and why do some fields interact more with the Higgs than others? So now that we have a more basic understanding on the Higgs, how do we look for it, and how do we find it? This is where the CERN part comes in. CERN, European Organization for Nuclear Research, is an organization that has the world's biggest particle accelerator called the LHC. And what do particle accelerators do? They accelerate particles and make them collide. You can do that too. Just grab a common object and smash it into the wall, but not at 99.999999999% the speed of light. So these two groups of protons are accelerated in two different motions, in two different directions, and in two separate tubes by these big magnetic fields, because protons are charged particles and can be deflected by magnetic fields. So they're successively transferred to bigger accelerators till they get to the 27 kilometer circumference monster called the LHC that makes these two groups collide in certain points. So physicists have these other big machines called detectors like the Atlas or the CMS so they can see these collisions. And by the immense amount of energy contained in these collisions, we're talking extremely small protons here, but accelerated at crazy speeds. These protons produce an array of other particles, like literally an explosion of particles, because particles can decay, transform in other ones. So the job of physicists is to look at all those different particles through computer programs and see if there's something interesting, like a Higgs boson, for example. And how do particle decays work? Well, for that we'll have to go back to our friends, the fields. If you remember that particles are mere vibrations in a field, a particle could transfer its vibration to another field, and thus causing that other field to vibrate, and thus changing into another particle. A weirder thing can happen is that a particle can transfer its vibration to an intermediary field, and then that intermediary field transfers that vibration to another field. So, in the intermediary field, no particle is actually created, so we just call that temporary vibration a virtual particle. Okay, but why was the Higgs so hard to find? Why such joy when the CERN announced on the 4th of July 2012 that a particle similar to the Higgs was found? Well, firstly, because being a heavy particle, it requires a substantial amount of energy to be able to produce it. And also, because being a heavy particle, it quickly decays in other particles, tiny fractions of a second after it's produced. Hence, all the expensive and huge machinery in accelerating particles and in detecting them. But secondly, and most importantly, because behind all this, there's one of the biggest collaborations in the entire history of mankind. Scientists from all over the world that dedicate their lives and give up all differences between them to reunite efforts and discover the secrets of our universe and the ultimate reality beneath our world, by building the very big and delighting ourselves with the very small.